Recall the equilibrium rule. When the sum of all the forces acting on an object is zero, no acceleration occurs. But in situations where the sum of the forces acting on an object is not zero, the object will accelerate. This acceleration depends upon the net force and the object's mass as given by Newton's second law. Both force and acceleration are vector quantities. The net force and acceleration are always in the same direction. We can write this as F sub net equals ma. When the net force is due to gravity alone, acceleration is g, that of free fall. Then F net equals mg. Let's put this information to use with this sample problem. A wooden block of mass m on a horizontal friction-free surface is accelerated by a string attached to an identical block hanging vertically from a small friction-free pulley, as shown. Identify all the forces that act on the two blocks by showing each force by a vector and labeling each vector. Let's begin with the downward force of gravity that acts on the sliding block, which we label mg. Also on this block is an upward support force, the normal force, equal and opposite to mg, that we label n. How do we know they're equal and opposite? Because the block isn't accelerating upward or downward. The string pulls the block to the right, which we show with this vector t. Tension T is the stretching force within the string, and it's the force exerted by the end of the string on whatever it's attached to. The vertical mg and n vectors cancel, leaving tension vector T, which accelerates the block to the right. The friction-free pulley doesn't change the amount of tension, only its direction. Although there's a 45-degree upward force by the table on the pulley and the pulley on the string, we don't show those forces here. We show only the forces that act on the blocks. For the identical hanging block, we draw the force due to gravity, mg, and upward vector t, of the same magnitude as vector t at the other end of the string pulling the sliding block. What we show are all the forces that act on the two blocks. Part B. Find the acceleration of the two-block system. We begin with A equals to focus on what we're asked to find. This is our starting point to finding a solution. Since we're looking for the acceleration of the two-block system, let's define the system with this white border. Note that the pair of t vectors are inside the border. Because of the pulley, they don't have the same direction, but they do have the same magnitude. These are effectively internal forces, which, in accord with Newton's third law, always cancel. Internal forces have no effect on the motion of the system. As said earlier, the equal and opposite forces mg and n on the sliding block also cancel. So the only external force that acts to accelerate the two-block system is mg acting on the hanging block. For acceleration of the system, we have, where we emphasize our system, and for our two-block system, the mass being accelerated is 2m. And we see that the system accelerates at half g. That's half the acceleration of free fall. This makes sense because the gravitational force on one mass is being used to accelerate two masses. Part C. Show that the string tension T is mg over 2 and not mg. Let's now consider just the hanging block as our system of interest. It's of interest because for this system, the force we're looking for, T, is an external force that is not cancelled. The only other force acting in this system is mg. So T acts upward and mg acts downward. From the sum of the forces equal mass times acceleration for the falling block, we get mg minus T equals ma, And recall that the acceleration is g over 2. And with a bit of algebra, starting by multiplying both sides of the equation by -1, we find that the string tension for the two-block system is half the weight of either block. What is interesting in this problem is that the weight of one block accelerates the masses of two blocks, and the tension in the string connecting the blocks is not the weight of either block, but half the weight of either one. What if you held the sliding block stationary so there was no motion? Then the string tension would equal mg. But if you release your grip and let the blocks accelerate, this tension decreases, as we've just seen. You can experience this firsthand. Hold a string that supports a stationary weight. You feel the tension. Now let the weight accelerate downward and you feel the tension decrease. Fascinating physics. I want to leave you with a question, two actually. Suppose one of the blocks were replaced by a feather. That's right, a feather with very little mass. Question 1. If the sliding block is replaced by the feather, how would the acceleration of the system compare with free fall acceleration g? Question 2. Suppose the falling block is replaced by the feather. How would the acceleration of the system compare with g? Can you see that in a similar two-block system, whatever the relative masses of the blocks, the acceleration can be a lot less or a little less than g, but in no case exceed g? Until next time, good energy.